Hello everyone, and welcome to my lecture about symmetry. In this lecture, we will discuss what symmetry really is and what identifiers we have to recognize how symmetric an object really is. Because all of us have an idea about symmetry. We recognize objects in everyday life and say that they are symmetric, whether it is a Greek temple, a human's face, or a mathematical object. We see it has symmetry. So this raises the question, what is symmetry actually? How can you describe to someone else what symmetry is? And for this, I will use an easy example. This is an artwork by the Dutch artist Escher. It's called Angels and Demons. And I'm asking you, well, a very easy question. I mean, we all recognize it is symmetric. It has symmetries. So we'll do a little experiment here. I ask you to look at the screen very carefully. And now, close your eyes. You can open them again. And I ask you, what do you see? Well, this is rather obvious. You see exactly the same. I'm not questioning your abilities to recognize that. The real question is, what could I have done with this object without you noticing? You think for a moment and you realize that there are various things I could have done. For instance, I could have turned this object over 120 degrees clockwise. And indeed, if I would have done that with this object, you would not have noticed. So this is a symmetry of the object. It is a rotation over 120 degrees. Are there others? Yes, indeed. Turning counterclockwise, so in this case, a rotation over minus 120 degrees, as mathematicians would say, is indeed also a symmetry of this object. Or there are more things I could have done without you noticing. Yes, clearly. I could have reflected the object over this vertical axis. You might wonder, a reflection, can you really do this with an object? Well, think of this object as a very small disk, which you can look at from both sides, and then you realize that a vertical reflection is just like a rotation over the axis in the third dimension, right? So yes, I can do this to this object. This is a vertical reflection. As we will say, it has mirror symmetry. Of course, you've spotted this reflection, and then you realize that there are two more reflections that I could have applied to this object. So we have spotted already 5 symmetries. Symmetries as things I can do with the objects without you noticing. There is a 6th one. The 6th one is so obvious, I hardly dare to tell you, but doing nothing is also something I could do without you noticing. Yeah, this is quite obvious, and you realize this is true for any object. So each object you think of has at least one symmetry. Every object is symmetric, namely the doing nothing symmetry. Mathematicians would call this the identity. Okay, so this object has 6 symmetries. So remember, and this is like the first thing I really want you to catch from this lecture, a symmetry, something you can do to an object without someone else noticing. And apparently this artwork has 6 symmetries. Now, there are a few things that I want you to observe with me. And the first one is quite easy. For each symmetry, there is an inverse, or an opposite, if you want to call it like that. If turning clockwise over 120 degrees is a symmetry, then obviously turning counterclockwise over minus 120 degrees is also a symmetry. And this is true anytime. Of course, a reflection is its own inverse. If you mirror over a vertical axis, well, the opposite of it, or going back to the original, is mirroring again over this same axis. But for instance, if an object has a symmetry turning it over 90 degrees, then turning back 90 degrees will also work. Okay, so for each symmetry there is an inverse. The second thing I want you to notice is that combining two symmetries again gives a symmetry. And this is maybe something you didn't realize at first, but if you think about it for a few seconds, this is actually quite logical. Because if you do something you don't notice, and you do another thing you don't notice, then the combining action is also something you don't notice. So two symmetries together give a symmetry. So we look at the previous object, at this Angels and Demons by Escher. So if we combine a vertical reflection and this rotation, we must get a symmetry. And let me think about it. What could it be? So I will highlight this small demon here. If I reflect it, I get here. If I turn now around, I get here. And this is exactly the same as I would get when I reflect over this line. So combining this first reflection and a rotation clockwise, we get another reflection. If I would have first turned and then reflected, you see I don't get the same result. Actually, in this case, the result is this reflection. So if I combine this vertical reflection with the rotation, I get another reflection, but it depends on the order in which I execute them, which reflection I get. So first, very important thing, combining two symmetries gives a symmetry, but applying symmetries in a different order can give different results. You may be not too surprised about this, but this is something you don't come across that often in real life. Okay, these observations are important, and especially because we have these first two things, mathematicians will call this a symmetric group. The symmetric group is, well, the set of all the symmetries and the rules about how to compose them. And because there are these first two properties, it is indeed a symmetric group. And actually, if you are talking to a mathematician about symmetry, they will ask, what is the symmetric group of this object? This is something we can work with. And this tells us actually how symmetric an object is. Now, we've seen the symmetry group of this artwork by Escher, and we've seen it has 6 elements. Okay, so symmetry groups can be finite, but there are also infinite symmetry groups. if I look at this checkerboard with white and red quadrangles, which stretches out infinitely in both directions, yeah, then it has infinitely many symmetries. For instance, moving each square one down and one to the right, as the first arrow indicates, yeah, this is something you can see. This is a symmetry, yeah, because every white quadrangle goes to a white, every red to a red. So this is clearly a symmetry of the object. But I can also move every square one up and three to the right. Also every white to a white, every red to a red, something you don't notice, symmetry of the object. So indeed, this symmetric group will be infinite because there are a lot, well, infinite number of these kind of translations that I can do to this checkerboard. So symmetry groups can be finite, can be infinite. Here we would see that the order when combining two symmetries doesn't matter, but we've seen in the previous example that it sometimes does matter. So symmetry groups tell us everything we need to know about an object. So I want to end my lectures by showing you a few more examples. On the first on the left is a hexagon, a regular hexagon. And well, you could wonder how many symmetries it has. Think about it for a moment for yourself. And you need to find 12. Then in the middle, we have a cube. Very nice cube. It has 48 symmetries. Think for a moment for yourself, where are these 48 symmetries? How can I find them all? And then the object on the end, which stretches infinitely up and down and has this pattern of moons. Well, you could ask yourself, which symmetries can I find? Of course, wait, not of course, but you will see it has an infinite number of symmetries. But which ones are there? Think about it. I hope you enjoyed and that you know a little bit more about symmetry now. Thank you.